Otherwise, so you may not know what we are doing here, right? So here first, before this slide, let me recall at this point our current situation. Yeah. What we are doing right now. Yeah. All right. We just developed these formulas. Yeah. So what are these formulas? Look at this. Number of I need to change my pen color. This one. All right. Yeah. All right. We just discovered number of internal nodes with any height. I hope you know the meaning of the height. Okay? Yeah. Yeah. Last time I explained, yeah, so let me draw the, a heap. Again, a simple heap. Yeah. Just refresh your memory a little bit. Yeah. In this simple heap, I want to draw nodes with height 1, h equals 1. Yeah. Remember, we come from bottom. Okay? Yeah. This bottom level, leaf level. Yeah. So that's the leaf level. Leaf level, we treated the height equals 0. Okay? Yeah. Now, height 1 node, this one, height 1 node. Okay? So you can see one edge reached leaf level. Okay? All right. But this one is not. Okay? This node is not. Because this node, starting from this location, you have several paths reach the bottom, several paths. But when we count the height, we use the longest path. Okay? We use the longest path. Longest path. Here, the longest path has edge number 2. So we treat this as height 2. Yeah. So in this way, this is the correct understanding of this height concept. Okay. Yeah. So then we develop the range for height h, the general formula. So those nodes spread in this range. Okay. Then we count the number of nodes. So this formula, number of nodes of height h. Yeah, height h. Okay, yeah, the formula. Yeah. With this formula developed, our next step, the goal. Yeah. So the goal, next step, estimate the cost. Estimate the cost of building a heap. The cost here means number of comparisons. Okay? Yeah. All right, yeah. So our next step, we need to do this estimate work. Yeah. Yeah. Our main tool, this is our main tool to use. Yeah. All right, yeah. So let's go to the next topic. B.2, building cost of a heap. Yeah. We are given arbitrary array. So our current status, given an arbitrary array. Yeah. So then we need to build a max heap here. Build a max heap. How do we build? Yeah. By the max heapify operations. Okay, yeah. And then, yeah, before I move to the next slide, let me draw a diagram. Yeah, because next slide we may not have that much space. So let me use the space here to explain one basic operation we will use when we build a max heap. Yeah. All right. Suppose this is a general heap. Okay. Yeah. General heap. Yeah. But it may not be a max heap. That means it may have some violations. Okay. Yeah. And we need to fix all the violations. Yeah. After we fix all the violations, we get a max heap. Yeah. So last time I give you one concrete example to show you how to build a heap from an arbitrary given array. Yeah. So remember the order. Yeah. So when we apply that max heapify operation in certain order. So what order? Bottom up, from right to left. Okay. Local triangle by local triangle, in that order. After we reach the top triangle, okay, the top triangle, yeah. So starting at the root, then we are done. Okay, after we process our last triangle with top at the root, so then we complete the building process. So that's what we did last. So here, I only want to explain one typical step. So what's that? Here, so let me consider arbitrary node in this heap. Okay, yeah, any node. Yeah. Here, we assume this node is dirty. Oh, sorry. Yeah, some, too sensitive. Yeah. All right. We assume this node is dirty. Okay. It's in gray color, dirty. That means there is a violation. Okay, there is a max heap property violation here. Okay, so this cross sign means there is a max heap property violation. Right here. Okay, all right. To remove this violation, we need to run our max heapify operation and consider the worst case. Yeah. Here we want to estimate the worst case. Worst case, yeah. The number of comparisons we need to do for the worst case. All right, yeah. Right, yeah. So for the worst case, I hope you can still recall how we did max heapify operation. Yeah. Remember, each triangle we compare its value with two possible child nodes, right? Left child node, right child node, compare the values. Yeah, so we have that pseudocode. Yeah, all right. The worst case should correspond to the longest path. Yeah, because at the end, the worst case, the gray node should reach the bottom following a path reaching the bottom, right? So here we want to choose a longest path. Longest path corresponding to the worst case, right? Yeah. Corresponding to the worst case. Okay? So here, the longest path. But how many comparisons do we need? Yeah. Remember our height definition. Yeah, so here, let me define the height. The height definition of this dirty node, height. Number of edges on its longest, one of its longest paths reaching the bottom. That's the height definition. Okay? All right. So then you can see the number of comparisons we need to do equals the number of edges. Okay? So that means the comparison number equals H. How about that? So can you see that? Yeah. For the worst case. Yeah. For the worst case, the number of comparisons you need to do the same as the H number. Okay? Yeah, H number. All right. All right. But every time when you recall, we do swap operation, right? We do swap operation. All right? Yeah. You know, all the way down to the bottom. Yeah. So when we do comparison, swap, you know, a lot of things, can we say the cost? So if we want to estimate the cost, if we just fix one gray node violation, the cost we do certain constant C times H. How about that? Certain constant, yeah. There is some constant, okay? There is some constant. Yeah. You need to do some work, but that work we can use a general constant represent. Yeah. So what we do, it's a constant C multiple times H. Yeah. And this one, remember if we use asymptotic notation, that is big theta of H. How about that? Yeah. So that's the amount of cost we need to pay. Yeah, we need to pay to fix one node violation. Okay, this is one node violation. Yeah. Then, in order to compute the building cost of this whole max heap, we need to fix violations everywhere, right? Yeah. So we need to consider all the possible violations. So our building cost, we need to accumulate all the max heapify fixing cost, total fixing cost, accumulating the fixing cost from all the possible dirty nodes. Okay? All the possible dirty nodes. Yeah, it's possible all the nodes are dirty. So we need to fix all of them. Okay? Fix all of them. Yeah. So that's our final building cost. Yeah. So let's do that estimate. So next slide, let us, based on our understanding here, so this problem I explained, so later we will apply the result we derived here to estimate the total building cost. Yeah. So now, combine the cost of all heights. Yeah. Now, it's not that hard after we understand. Single node cost. Yeah. Fixing single dirty node cost. Then combining all the cost. Yeah. Pretty straightforward. Yeah. Cost of max heapify for all nodes of height h. Yeah. First, let's look at the height h. Yeah. Because height h, there are many height h nodes, right? Yeah. There are certain number of height h nodes. Let's look at the subtotal cost fixing all the height h dirty nodes. How about that? Yeah, the first step. Only on one height number. Yeah. Next, then we accumulate all heights. Yeah. The cost from all heights. Yeah. All right. What is this number? This is not number. Okay. Yeah. Here, ceiling function. Ceiling function. Remember, the number of here we call the number of nodes of height h. The formula is not exactly this one. The formula is floor, ceiling, yes, yeah, floor, okay, and over 2 to the h minus and over 2 to the h plus 1, okay, yeah. So this is exact formula. This is exact formula, okay. Okay, exact formula. And because this formula, sometimes it may not be convenient to use, so we like to estimate. And this formula is not exact. This is estimate formula. This formula is slightly larger than the exact number. Okay? Yeah. So, because in this way you may see some different expressions. Yeah. So when you study the notes, why we use a different expression? Yeah. The reason is when we do estimate, sometimes we like to use, a convenient expression, but that is a little larger than the exact expression. Yeah. That happens a lot. Okay. All right. Yeah. So let me look at the Elroy's question. For the swap, shouldn't that be H as well, since we would be swapping? Yeah, all right, yeah. So for Elroy question, so that's why I count as C times H. Yeah. Now you're talking about the swap operation, right? Swap operation contains a few assignment operation, right? Assignment operation. Okay? Ops. Yeah. So when we count assignment, there is some certain cost. Okay? Yeah. But assignment cost, if you want to do some accurate, estimate, here, let me write a little more. Okay? Let me use C1H for comparisons, okay? From comparisons, okay? Comparisons. C2H for assignments. And so on, okay? Yeah? So when you include the swap, how about our total cost C1 plus C2 parenthesis times H? And we make this C. How about that? Okay? So if you want to do better estimate, we can do in that way. Okay? We split, swap, and the comparisons. Yeah. Yeah. So one swap equals several assignments. And the data copy, right? Last time I explained the data copy, yeah? So at that point, the data copy, so you can use C2 constant. C2 constant, you know, for the data copy. Yeah? And the C2 could be much larger than C1, yeah, because comparison, we know comparison is very fast, but data cost is very slow, right? Last time I talked about the satellite data. If you need to copy satellite data, then the C2 number could be very large, okay? Dominant. It's a dominant term in the C, yeah, in that C, okay? All right, but overall, we only need to know there is a C, okay? There is certain constant C there, yeah. So we just use some abstract constant C, yeah. All right, yeah. But the H part, the same, okay? H part, the worst case, still H, yeah. All right, yeah, so here we have, but this is for one height H, but we need to go through all height H numbers. Yeah. So we need to do summation from all possible heights. Yeah. So we need to write yeah, and also, yeah. So each one, big O and a big theta. Yeah. Although here I use big O because we only look at the upper bound. We do not look at the lower bound. Okay. So if we only look at the upper bound, big O, big theta, you know, the same. Okay. Yeah. Only when we look at the lower bound, then they are different. Yeah. But here, we want to estimate the upper bound of the total cost, not lower bound. Okay, upper bound. Yeah. So we are interested in the upper bound. Yeah. So it's okay. We use the big O notation here. Okay. All right. The heights from 1 to floor function of log base of n. Yeah. 1. Yeah. Yeah, definitely from 1, from the nodes, yeah, because those leaf nodes, for the leaf nodes, we do not need to do anything, right? Yeah, leaf nodes, they're already at the bottom. Yeah. So it's impossible there is any dirty leaf node, right? Yeah. The leaf node cannot be dirty, right? Yeah, yeah, because no child node. Okay, the dirty only when we compare the value parent node between parent node and a child node, then we can find a violation. So for any leaf node there is no violation. Okay, max heap property violation. Yeah, so the leaf node we do not need to do any work. Yeah, so we start to do the fixing work for height H node. Height 1, yeah, height 1 is the smallest height number we need to do the fixing work. Yeah. The largest at the root height floor function of log base 2 of n. So this corresponds to the root. The root. Okay, yeah. All right. So now when we do summation, yeah, so our summation, yeah, becomes this expression. Yeah. So this, I hope you are familiar, you know the meaning of this big sigma notation. Yeah. Summation. Yeah. Yeah. Lower limit 1, upper limit floor function of log base 2 of n. Yeah. Then ceiling function times, yeah. So here, because we look at the upper bound, you can consider certain C constant times H. Yeah. Because asymptotic notation, it's hard to do math calculation on asymptotic notation, right? Yeah. So it's better, so we can, you know, use this expression, constant C times H. Yeah. All right. This summation. Yeah. This summation, because the seeding function not very easy to handle, right? Seeding function, yeah, there is a small difference, but that small difference hard to control. Okay, we do not know how large is that small difference. Yeah, yeah. But in our estimation formula, let us remove the seeding function and replace it by a larger expression. Yeah. Larger expression plus 1. Yeah. Because that difference should be less than or equal to 1. Actually less than 1, right? It can, yeah, even not equal to 1. But here we are very generous. So we enlarge it plus 1. Yeah. Add that plus 1. Okay? Yeah. Larger. In this way, we remove the seeding function, so our math calculation will be much easier. Yeah. All right. So then there are two terms. Yeah. First and the second term. So let's split those two terms. Yeah. The constant, the one part should be easy. Okay. One part should be easy. Then we need to estimate the first term. Yeah. So this is the first summation and the second summation. Yeah. So second summation, very easy. Yeah. So let's look at the second summation. Yeah. All right. The second summation, yeah, let us replace it by CH. Yeah. Otherwise, if we use big O, yeah, we do not feel very comfortable using big O in our calculation. Okay? Yeah. So we can use the C. Yeah. Yeah. I mean, so here you just understand this big O we treat as certain constant multiply things in the parentheses. Yeah. So this formula. Yeah. All right. This one we apply the summation formula 1 plus 2 plus dot 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 plus k equals 1/2 k plus 1. Okay. Here this k is that log base 2 of n floor function, but we just replace floor function, remove the floor function by a little larger expression. Yeah. Because in our estimate, it's not necessary our expression must be an integer expression, right? It's not necessary. Okay? So we remove the floor function without any problem. Yeah? Because our estimate expression is not necessary to be an integer expression. No. Yeah. We just want to know how large is the value. Yeah. If it's a non-integer expression, it's fine. Yeah. We just want to know how large is that number. Yeah. So we remove that floor function. Yeah. So we get this expression, and this expression is in big O of log n parenthesis square. Okay? Square of, it's not a square of n. It's square of log base 2 of n. Much smaller, right? Yeah. So let's leave this second summation here. Okay? That's for the second summation. Our main work is at the first summation. First summation. Okay? All right. The first summation, the main term, yeah, you can still treat, this big O, we use a constant C to represent it. Okay? Yeah. All right. So then, in this summation, yeah, we need some technique. Yeah, let me monitor the time. Yeah. All right. Yeah. I need to control the time, so not spend too much time. Yeah. All right. Yeah. Okay. Yeah. Let me go a little faster. Yeah. All right. In this expression, which number is which number never changes, which other than C. We know this constant C never changes in the summation. Other than C, can you tell me in N and H, which one does not change when you run through all the terms in the summation? All the terms in the summation. Yeah. N never changes. H changes. Yeah, because for different term, the H number is different. The first term, H equals to 1. Second term, H equals 2, and so on. Yeah. But the N, this N number, for all the terms, N number never changes. If N number never changes, we can factor it out of the summation. Yeah? We just treat it as constant. It never changes. We can factor it out. Okay? Yeah. All right. So here we factor it out. Okay? Although this constant C can be carried out with this M. Yeah. So then the summation part, we only need to look at the H related terms. No N, right? Yeah, no N. Yeah. All right. So next, let's estimate the summation. But the upper limit, it's a log function. Log function, not easy to handle, right? Yeah. Log function is not easy to handle. But can we enlarge the upper limit to infinity? Enlarge it. Okay, enlarge it to infinity. Okay, here you can see we are very generous. Yeah, we are very generous. We add more cost. Yeah, so we use larger expression to estimate, a very generous estimate. Yeah, but don't worry. Yeah, although it looks on paper generous, but actually we didn't add too much. Okay, we didn't add too much. The tail part, yeah, the tail, yeah, the summation. So we add a long tail. Okay, goes to infinity, long tail. That tail part is very small. Okay, very, very small. Yeah. So that means we still put the whole summation under control. Yeah. Otherwise, if we are too generous, probably the total cost, the total summation is out of control. Okay, that's very bad. Yeah. But here we put it under control. Yeah. All right. So here you can see, basically we need to calculate this summation. Okay. Yeah. So this series. Yeah. Calculate this series. Yeah. Yeah. To calculate it here, because there is a very smart trick that I want to show you. Yeah. Not very hard. Yeah. But pretty smart. So I want to show you how to calculate. Calculate the summation here. Yeah. First, we observe there is a property, the denominator. So if you look at all the fractions, the denominator numbers are power of 2. Yeah. Consecutive power of 2 numbers, the denominator. Okay? Yeah. All right. So if you multiply each term by 2, think about each term by 2, yeah, 2 cancellation after 2 factor cancellation, the denominator still power of 2, right? Yeah, after you cancel 1, 2 factor, the denominator still power of 2. Yeah, that property is very useful. Okay, so we want to use that property to help us make this summation easier. Yeah. All right. So let's look at the. Now we double S. Yeah. Double S, we multiply S by 2 both sides of the equality. So we multiply 2 at the right hand side. So you can see the denominator 2 squared becomes 2 to the first, 2 cubed becomes to 2 squared, and so on. Still power of 2. Yeah. You just reduce the exponent number of that power of 2 by 1. Yeah. Yeah, but still, power of 2 number, then you can see these two series, yeah, you can see, especially if you look at the corresponding power of 2. Yeah, for example, the denominator 2 cube and 2 cube here. Yeah, you just look at the, the like terms. You compare the like terms. So you can find some special rule there. Yeah. When you compare the like terms, you can see this interesting rule. Yeah. The lower one is 1 more than the numerator. Look at the numerator, the difference of the numerator. The lower one is 1 more than the upper one. Okay? Yeah. So, and it's true everywhere. Okay? When you compare the like terms, the difference of the numerators equal constant 1. That's a nice property. Okay? Yeah, so let's apply this property. So we can take a difference between these two equalities. Yeah. So we use the lower equality to subtract the upper equality. Yeah. So then the left hand side we get an S. The right hand side, this time you can see a very simple series. Yeah. So this is a geometric series. Yeah. The summation of this geometric series, power of 2. Okay. The numerator all 1. Yeah. All 1. Yeah. So by the formula, we can easily calculate equal to 1. Yeah. So do you know the formula? Infinite series, the calculation. Yeah. So the infinite series. Yeah. So here, let me recall. Suppose we have a series. The first term is A. Second term, A times R. Common ratio, R is the common ratio. Next term, R squared, and so on. Dot, dot, dot. Okay? To infinity. Okay? Yeah, to infinity. All right. Yeah. So this series, the formula is A, okay, the first term, over 1 minus R. Yeah. So here, the R, absolute value of R should be less than 1. Then it's convergent. Yeah. If the absolute value of R is greater or equal to 1, it may not be convergent. Okay? So it may not be convergent, then the summation does not exist. Okay? Yeah. So only when absolute value of R strictly less than 1, then the series is convergent. Yeah. Here, our R, here, our A equals to 1. Yeah? Our A, actually, the first term, our A equals 1/2. And our R equals also 1/2. 1/2 positive, strictly than 1, so we know this series is convergent. Yeah. So then we can apply the formula here. A 1/2 over 1 minus R 1/2 equals to 1. Okay? Yeah. So we apply that formula. We get a 1. Yeah. All right. Yeah. Now let me look at the Elroy question. Could you repeat how you use the 1 more on the bottom property to cancel the fact that the numerators were incrementally going up? All right. So the use the 1 more. Yeah. So 1 more about the numerator on the bottom to cancel the the numerators incrementally going up. Yeah, all right. So so here I jump a little faster. All right. Look at the red circles. All right. Yeah. So when we do cancellation, so when we do subtraction, left hand side 2s minus s. That's easy. The right hand side, okay. Right hand side, you use the bottom row minus the top row. Yeah. So here, I need a little space here. Yeah, let me see where can I find a space. Oh, good. I have a lot of space here. All right. Yeah. So I can use the space here. All right. All right. Yeah. So when we use the bottom row to subtract the upper row, all right, we do this way. The first term, 1/2, there is no corresponding upper number paired with it, right? Yeah, the first number in the bottom row, we cannot find, or if you really want to find one, there is an invisible 0, right? But it's not necessary, okay? Yeah, it's not important. But after this one, then we do grouping in red circles. So this is our grouping way. Grouping way. The red circle gives us how we group those numbers. So grouping, we use parentheses. Okay? Okay. 2 squared minus 1/2 squared. The first group, second group, in the second red circle, 2 cubed minus 2, and so on. Okay? Yeah. And we use a representative term. So this red circle, we use it as the general group. This is our general group representation. So we use it as a representative. Okay? All right. So h plus 1 over 2 to the h plus 1 minus h 2 to the h. Okay? Da. All right? Yeah. All right. So then, plus 1. Okay? Plus 1. Okay? Plus 1. Plus 1, we get this, we can simplify to 1 over 2 to the h plus 1, right? Yeah. H plus 1, here you can see slightly different from 2 to the h, but the h number is a variable. It can be any number, right? Yeah. So h plus 1, its previous term, if you see the h plus 1 here, its previous term is 1 over 2 to the h, right? Yeah. So we can use its previous h there. Okay? Yeah. But what you can see in each pair of parentheses, you get a reciprocal of power of 2, right? Yeah. The numerator always 1. Denominator always power of 2. So we have reciprocals of power of 2. And reciprocals of consecutive power of 2 numbers. Yeah. So that's what we get. Okay? Yeah. All right. Yeah. So after that, now the conclusion. So our conclusion. Oh, sorry. The conclusion, because this s equals 1. So here, remember, after we factor out c and n, we have a summation. We have a big summation. That summation s equal to 1. Okay? Equal to 1. So then only c times n remains, but c times n we can represent big O of n, right? Yeah. C times n we can represent it as a big O of n. But this is the first summation term. First summation term. Okay? Yeah. This is the second summation term. Okay? But you can see the first term dominates the second one, right? The first term, big O of n, the second one, log base 2 of n, although square, but it's log base 2 of n. Okay? So the first term dominates the second term. Okay? Dominates, so that means we can drop the second term. Too small. Compare it with the first term, it's too small, so we drop it. Okay? So we only keep the first dominant term, that's big O of n, that's the building cost. Yeah. Now the conclusion. How much cost when we build a heap of array with array size n? Certain constant times array size number, C times n. That's the building cost. If you do not want to use the asymptotic notation, yeah, so we just use certain constant multiply size number n. That's the building cost. Okay? Yeah. Yeah. That is not too high. Yeah. So that is not too high. Yeah. So we have no problem. We take it. Yeah. So we use this much cost to build a max heap. Then the next step, we can run the heap sort. We can run the heap sort. Yeah. And it is pretty straightforward. Yeah. Running the heap sort. Yeah. Pretty straightforward. Yeah. So we can quickly get it. Yeah. Heap sort efficiency analysis. Yeah. All right. So here, let me show you the idea of heap sort. Yeah. Use a diagram. Use the simple diagram here. Yeah. All right. Yeah. So here we assume we build a max heap. So this is a max heap already. After we use the cost big O of n, after that, we have a max heap. So we run the heap sort on this max heap. Yeah. And before we run it, we have this fact. The largest element is at the root. Yeah. Yeah. Otherwise, you have a violation. So the largest element must be at the root. Yeah. If the largest element is at the root, can we put the largest element in place immediately? We know the location of the largest element at the end of the array, right? The largest element, if we use the final sorting positions, the largest element must appear at the end. So we know its location. Then we just put it in place immediately, right? Yeah. So the first thing we will do, we will put the largest element in place by a simple operation. The simple operation is swap operation. We swap the root with the last element in the array. Yeah. Because this max heap corresponds to array. So here I also draw a line for this array. The root is at the first position. Yeah. First position other than 0. Okay? We exclude index 0. Yeah. The first position is 1 here. Okay? Yeah. 1 and n at the end. Yeah. Yeah. But then now we use one swap operation to put it in place. Yeah. Okay? Yeah. Then how about swap the first element, first element here and the last element at the end, one swap operation, we put one element in place. But because this node after the swap, it's at the root position, and it's very likely it is dirty, right? Yeah, there is a violation at the root. Yeah, yeah, sure. Yeah, there is, very likely violation occurs at the root. So we need to run max heapify operation to fix it. Yeah. But when you run max heapify operation all the way down to the bottom for the worst case, yeah, the gray node, all the way down along the longest path to the bottom, yeah, the cost is log base 2 of n, right? Yeah. Log base 2 of n. So you recover the max heap next, yeah, because we have to recover the max heap, right, with this much cost, yeah, fixing cost. This is the fixing cost, okay? Fixing cost, okay? Yeah. After this much fixing cost, we recover the, the current heap to the max heap again, so we can put another element in place, right? Yeah, because this time the element at the root must be second largest. Yeah, must be second largest. So then we put second largest element in place in the second round. Yeah. Then the next round we need to, fix the dirty node at the root another time, and then put another third element in place, and so on. Okay? All right. So here the operation. Yeah. First step, we swap A of 1 and A of n, and put one element, largest element, in place. After that, we need to recover the heap structure. Actually, yeah, not the heap structure. We need to recover the max heap structure. Yeah, not just heap. Yeah, max heap property. Okay, yeah, structure by running this max heapify operation. Okay, yeah, all right, yeah. So yeah, so then we do the iteration. Yeah, so like this. All right, yeah, we do iteration. Yeah, so you can see we can put all elements in place. Yeah, but if you do it this way, what is your total cost, right? Yeah, what is your total cost? Because our goal, the total cost must be big O or big theta of n log n. That's our goal. Okay. If your total cost is much more than this goal, this number, then we cannot use this sort. Yeah. Remember, at the beginning, we need to satisfy 3 requirements. So this is one of the requirements. Okay. So next, we need to estimate. Yeah. All right. Yeah. So here, first I describe the procedure of heap sort. Yeah. First, build a max heap, the step. Second, we run a for loop. Okay. The for loop, the counting variable I, top down. Okay. From n down to 2. Yeah. We do not need it down to 1, right? Because after we down to 2, the last element is forced to be in place, right? Yeah. After you put n minus 1 elements in place, so the last one is forced to be in place. So we're done. So that's why I from n down to 2. Yeah. Then each round inside the for loop, each iteration, we swap A of 1 and A of I. Okay? Yeah, A of I. The last element in the current max heap. Okay? A of I, so this is the last element. in the current heap, in the current max heap. Okay, yeah, it must be a max heap. Okay, so we do swap and put one element in place and put this element in place. Okay, all right. After that, we need to fix it. Okay, now before we do that, we need to reduce the heap size. Okay, yeah, because after you put one element in place, your heap is reduced. Your heap size is reduced by 1. Yeah. We should exclude all those in-place elements in our current heap. Okay, so we need to update our current heap size by 1. Yeah, reduced by 1. Okay, after that we run the max heapify function another time. Okay, run it another time. Yeah, all right. Yeah, so in this way, so you can see after we complete this function, we get the whole array sorted. Yeah, but we need to estimate the total cost. Yeah, all right. So here, if I use a simple diagram, it should be very simple. Yeah, diagram. Yeah. All right. You can see when we run the max heapify, because when we do swap, that is just one operation. If you use some constant, c times 1 operation, right? Yeah, certain constant c times 1 operation. Okay, so that's the small part. Then the larger part, you need to run the max heapify operation. So that is, you start from the root. You start from the root and you reach the bottom. So the cost number, the cost expression is the log base 2 of the number of elements in the current heap. Okay? Yeah. So the next one is log base 2 of n minus 1 and so on. Okay? Every time the last one is log base 2 of 2. Yeah. And this estimate, there is a simple way to estimate it. Yeah. Because think about how many terms do we have, right? The number of terms, you can say log base 2 of n the number of terms, n minus 1, right? Yeah, yeah, because this term corresponds to n. Next term corresponds to n minus 1, all the way down to 2, but the 1 is missing, right? 1 is missing, so the number of terms n minus 1, but we can drop that minus 1, we just use n here, okay? Each term less than or equal to log base 2 of n, right? Yeah. So each term, we just use log n to represent it. Yeah. So then the total cost should be less than or equal to big O of n log n. Yeah. Here, we use very rough estimate. Our estimate is very rough. Yeah. But we get this n log n. Okay, that's good enough. Yeah. So we are very confident that the Heapsort is in this category. Okay, capital O of n log n category. Yeah. So we're done. Yeah. So we complete the Heapsort. Yeah. Here, the main reason why we. So from the whole topic, so we finish this Heapsort topic. The whole topic, the goal of this whole topic, we want to learn the power of data structure. Think about, without the special data structure heap or max heap, you may not be able to solve this problem, right? 3 requirements. Sorting data with 3 requirements, it's hard to how to find that solution, right? Yeah. So the solution relies on the special data structure max heap. Yeah. Max heap data structure. Okay? Yeah. Yeah. So you get an idea. Yeah. The importance of special advanced data structure. Yeah. All right, so we finished this topic. Yeah, good. Okay. Yeah. All right. Yeah. Yeah. So here we are very close to the break time. Yeah. So in my original plan, I planned to use 30 minutes, but we used 1 hour to finish this topic. Yeah. So the next one. Yeah. So one student asked me, there is one question, pretty challenging. Pretty challenging. So here, I will record in the video. Yeah. So here I just say something. Yeah. The last question, question number 25. Yeah. 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 Question number 25. Yeah. Because I put the hardest question at the end. Yeah. So this is the most challenging question in this assignment. Yeah. This one, we have a 6-element array for arbitrary given 6-element array. Okay, yeah. And we need to find the third largest. Okay, all right, yeah. With the minimum number of comparisons for the worst case. Yeah, all right. So this one, when you answer this question, so you need to recall one of our midterm questions. We have a similar midterm question we just did. Okay, so you can go back study that one. In the midterm question, do you still remember we sort 6-element array with 10 comparisons? Yeah, you look at my solution file. The solution, the best solution is 10 comparison. If you use that lower bound number, remember the lower bound number log base 2 of 6 factorial, you also get 10 comparisons. Yeah. But our midterm question, you need to provide the sorting detail steps. Many people just apply this formula to give me 10 comparisons. Okay, that's correct. But you cannot get full credit. You can only get half of the credit because you didn't tell me how did you sort it. I need that information. I need the sorting details. Okay, yeah. My solution file tells you how to sort it. Yeah. Here, based on this question, because with 10 comparisons, we can already sort 6-element array. That means we can get this third largest element after we sort it, right? So that means there is a 10 comparison solution by sorting. Yeah. To solve this problem, so your target should be better than 10 comparisons. That means you should target non-comparison solution. Without sorting, if you can get a 9 comparison solution without sorting, then you are there. Yeah. You're there. Yeah. If you do worse than 10 comparisons, then just do the sorting. Do the sorting. You have the 10 comparison solution better than your 11 comparison solution. Some students may get 11 comparison solution. Then you would rather use the sorting based solution. Okay? Yeah. Only when you need to beat that 10 comparison solution, then you can do a non-sorting based solution. Yeah. You do not have to sort it. to find the third largest element, you do not have to sort it. Okay? Yeah. So let me just stop here. Yeah. So I want to give you a more than 10-minute break. So, but the remaining part I will talk about in my hint video. Okay. I will still create a hint video for this last challenging question. Okay. Yeah. Because I need to give you 2 examples for this question. Yeah. Two related examples for this question. Yeah, because this is the hardest question of this assignment. Okay? Yeah, so I will give you more information. All right, so let's take a break.